What would really happen in the first 7 days after the nuclear powers push the red button? The answer isn't found in blockbuster movies, but in the cold, hard calculations of science. It's a sequential scenario of collapse, beginning with a blinding moment and ending in perpetual darkness. The first second isn't a sound, but a silent light. Hundreds of artificial suns ignite over major cities, brighter than the real sun, turning concrete to dust and people into permanent shadows on walls.
In the blink of an eye, millions of lives become nothing more than a thermal memory. Immediately after, the shock wave hits, an invisible wall of air moving faster than sound, flattening everything in its path. Skyscrapers shatter like glass.
But the most silent destroyer comes from above. The electromagnetic pulse, or EMP, a byproduct of high-altitude explosions, sweeps across continents. It doesn't harm humans directly, but it kills our civilization. The global power grid collapses, cars stop working, planes fall from the sky. Every electronic device, from the phone in your pocket to the control systems of nuclear power plants, becomes a useless brick. In an instant, humanity is thrown back to the Stone Age. On the second day, the black rain begins to fall. This isn't water. It's radioactive fallout, the ashes of incinerated cities carrying invisible death. Anyone exposed to it receives a slow, painful death sentence from acute radiation syndrome. There is nowhere to hide. The wind will carry these deadly clouds across the planet, poisoning the soil, the water, and the air. The concept of a safe zone is merely an illusion. From the third day, an even more terrifying phenomenon begins: nuclear winter. Hundreds of millions of tons of soot and ash from colossal firestorms are injected into the stratosphere, forming a thick black shroud that envelops the entire Earth. Sunlight cannot penetrate it. The midday sky becomes a permanent, gloomy twilight. Global temperatures begin to plummet, not by degrees, but by tens of degrees Celsius in just a few days. Summer turns into a frozen winter. Rivers freeze, snow begins to fall in the tropics, all crops on the planet wither and die. The global food chain completely collapses. By the 7th day, the world we knew no longer exists. There is no government, no law, no communication. Hospitals become morgues without power and medicine. Supermarkets are empty. Panic and desperation lead to a total breakdown of social order. Those who survived the blasts and the fallout now face new enemies: starvation, the cold, and their fellow human beings. 7 days. That's all it takes to turn our green home into a frozen tomb, shrouded in darkness and despair. Thousands of years of civilization erased. And the only question left in the minds of the survivors is not, how do we rebuild? But is there anywhere to escape this hell? Amidst Mars, space stations, and distant planets, why does the moon emerge as the #1 hope? In the ashes of a dying world, as Earth's sky is shrouded by nuclear soot, the answer lies not in grand ambitions, but in brutal practicality. Choosing the moon is not a choice of luxury, but of survival. And the first, most crucial reason is distance. Just 3 days. In a time of desperation, 3 days is a miracle. Mars, with all its potential, requires a journey of 6 to 9 months. That's a one-way trip into the unknown, with no chance of turning back. No possibility of quick resupply from a collapsing Earth. In contrast, the Moon is like a lifeboat just off the coast. The short distance allows for shuttle flights, transporting experts, delivering critical equipment, and maybe, just maybe, conducting emergency rescue missions. In the initial phase of the Exodus, when every bolt, every microchip is as precious as gold, the ability to return to Earth to salvage what remains is an immeasurable strategic advantage. But proximity isn't enough. A shelter needs power. And this is where the Moon literally shines. While Earth plunges into the cold darkness of nuclear winter, the Moon bathes in endless light. There is no atmosphere, no clouds, no weather. Solar energy becomes an almost infinite, stable, and powerful resource. Solar panels stretching across the gray surface can power the domes, the life support systems, and the manufacturing plants. Energy is the lifeblood of civilization, and on the Moon, that lifeblood flows abundantly. However, energy is meaningless without the most essential element for life, water. For decades, we thought the Moon was as dry as a cosmic desert. But then, science delivered a game-changing discovery. Hidden deep within the permanently shadowed craters at the poles exist billions of tons of water ice, a treasure frozen over millennia. This is more than just drinking water. Through electrolysis, water ice can be split into hydrogen and oxygen. Oxygen to breathe, filling the habitats. And hydrogen and oxygen together are the most powerful rocket fuel we know. The implication of this is monumental. It transforms the Moon from a final destination into a way station. Humanity would no longer be tethered to Earth's gravity well. We could mine the ice, produce fuel on site, and turn the Moon into a gas station for the solar system. Finally, when you combine all these factors, close proximity, endless energy, and in situ resources, a larger picture emerges. The Moon isn't just a place to escape to. It's a springboard, a platform for humanity to reach further. From here, in a low-gravity environment, building and launching massive spaceships would be vastly easier and more economical. The Moon would become a space shipyard, the departure port for missions to Mars, the asteroid belt, and beyond. It's where our species learns to truly live in space, not as temporary visitors, but as cosmic citizens. So the answer is clear. Amidst the chaos and collapse, the Moon is not the perfect choice, but it is the only viable one. It is the closest, brightest, and most promising beacon in the apocalyptic night. How do you build a city from scratch on a world with no air, no liquid water, and extreme temperatures? This question is not just an engineering challenge. It's a question about the nature of life and the limits of human ingenuity. We are not simply moving to a new location. We are attempting to plant the seed of life into a barren rock suspended in a cold vacuum. The lunar surface is one of the most hostile environments imaginable. By day, the temperature can soar to 127 degrees Celsius, hot enough to boil water. By night, it plummets to minus 173 degrees Celsius, colder than anywhere on Earth. And on top of it all, there is no atmosphere for protection. The surface is constantly bombarded by micrometeorites traveling at tens of thousands of kilometers per hour, and bathed in a lethal shower of radiation from the sun and deep space. Building a house here is not like building one on Earth. It's like building a permanent spaceship, a fortress against the universe itself. So, what would the blueprint for Project Genesis 2.0 for humanity's first city off Earth look like? The first and most urgent solution is shelter. We cannot live on the surface. At least, not at first. The shielding required to protect against radiation would have to be meters thick, making construction incredibly expensive and complex.
But fortunately, the Moon has provided us with a natural, elegant, and incredibly effective solution: lava tubes. Billions of years ago, when the Moon was geologically active, rivers of molten lava flowed beneath the surface. As the outer lava cooled and hardened, the molten core inside continued to flow, leaving behind vast, hollow tunnels. Some of these lava tubes are estimated to be up to a kilometer in diameter, large enough to house entire cities. These natural caves are perfect shelters. The dozens of meters of rock and lunar soil above provide a nearly absolute shield against radiation and meteoroid impacts. The temperature inside them is also extremely stable, hovering around -20 degrees Celsius, which is far more manageable than the nearly 300-degree swing on the surface. The first phase of a lunar colony would involve deploying autonomous robots into these lava tubes, sealing the entrances, and filling them with breathable air, creating the first safe living spaces. But we cannot live underground forever. To expand and thrive, we need to build on the surface. And this is where the second breakthrough technology comes in: 3D printing with lunar soil. Transporting construction materials from Earth is prohibitively expensive. Every kilogram of cargo launched into orbit costs thousands of dollars. Instead, we will use the one thing that is available everywhere on the Moon: the fine, sharp dust that covers the entire surface, known as regolith. Giant, autonomous 3D printers would collect this soil, then use concentrated solar energy or lasers to melt the dust particles, centering them together into a solid, ceramic-like material. Layer by layer, we can print walls, domes, roads, and landing pads. These structures, built from the very material of the Moon, would be the outer shell for pressurized habitats inside, providing an additional, robust layer of protection. Once we have safe shelter, the next challenge is to create a livable environment. We need air to breathe, water to drink. On the Moon, none of this is readily available. The solution lies in a concept called a closed-loop life support system, or LSS. Imagine a miniature biosphere, a perfect recycling system where nothing is wasted. Every breath you exhale, releasing carbon dioxide, would be captured. Systems like the Sabatier reaction would use energy to split the CO2 into oxygen for you to breathe again and carbon. Urine and wastewater would be filtered and purified with near 100% efficiency, returning as pure drinking water. Even the moisture in the air from sweat and respiration would be reclaimed. In such a closed system, every molecule of water, every atom of oxygen, is a precious resource that cannot be lost. It is a delicate dance of chemistry and biology, a complex machine that must run without fail, because even a minor failure in the system could lead to disaster. But humans cannot live on recycled air and water alone. We need food. And here we face one of the greatest challenges: space agriculture. Obviously, there are no fields on the Moon. Our farms will have to be located deep underground, inside lava tubes or shielded structures, to protect the crops from radiation. Instead of sunlight, they will be bathed in the purple and red light of thousands of high-efficiency LED lamps, tuned to optimize photosynthesis. We will not be planting in soil in the traditional sense. The Moon's regolith not only lacks essential organic matter, but also contains toxic compounds like perchlorates and heavy metal shards. Planting directly in it is impossible. Instead, we will use hydroponic systems where plant roots are submerged in a nutrient-rich mineral solution, or aeroponics, a more advanced method that mists the roots directly with nutrients.
These methods use up to 90% less water than traditional agriculture and allow for precise control over the nutrients delivered to the plants. Potatoes, lettuce, soybeans, wheat, energy-dense and nutritious crops will be the foundation of the lunar diet. Organic waste from humans and plants will be composted to create fertilizer, closing the nutrient loop. All of this, habitats, life support systems, farms, requires one thing: energy, a lot of it. Fortunately, the Moon has a major advantage. With no atmosphere or clouds, its surface receives abundant and uninterrupted solar energy for 14 continuous Earth days. Vast solar farms stretching for square kilometers would be installed near the Moon's poles. At these locations, like the rim of Shackleton Crater, some peaks are in near-constant sunlight, providing an almost perpetual source of power. But the Moon also has a 14-day-long freezing night. To ensure a stable power supply, solar power will be supplemented by small, safe, and efficient nuclear reactors. These new-generation fission reactors can operate for years without refueling, providing the essential baseline power to keep the lights on and the life support systems running through the long lunar night. This energy won't just be for life support. It will be the engine of a true industrial revolution. This is the final and perhaps most crucial piece of our blueprint: in situ resource utilization, or ISRU. ISRU is the philosophy of turning the Moon from a place of mere survival into a place of growth. Instead of shipping everything from Earth, we will learn to mine and use what the Moon itself provides. The regolith, besides being a building material, is rich in oxygen, making up about 45% of its mass. Processing plants would heat the regolith to release this oxygen, providing breathable air and, more importantly, a key component of rocket fuel. Metals like aluminum, iron, and titanium can also be extracted to manufacture tools, spare parts, and new structures. But the Moon's greatest treasure is hidden in the permanent darkness of the polar craters. Here, where sunlight never reaches, the temperatures are so cold that water ice has persisted for billions of years. Mining rovers would excavate this ice, melt it for drinking water, and split it into oxygen to breathe and hydrogen for fuel. Water from the Moon is the ultimate game changer. It not only ensures the self-sufficiency of the colony, but also turns the Moon into a solar system oasis, a gas station. We can produce rocket propellant right there, refueling spacecraft for missions further out to Mars and the asteroid belt at a fraction of the cost. Thus, the blueprint for Genesis 2.0 emerges. It is a complex and interconnected ecosystem. Habitats underground and on the surface built from lunar rock. Air and water recycled endlessly in a closed loop. Food grown in artificial gardens. Power supplied by both the sun and the atom. And nascent industries beginning to tap the wealth of this new world. This is not a distant dream. Every technology we've discussed is based on solid scientific principles and is currently under development right here on Earth. It requires a colossal effort, an iron will, and unprecedented global cooperation. But the blueprint is there, waiting for the builders of the future. To safely get the first 10,000 people to the Moon, do we need a logistical miracle or an unimaginable sacrifice? The terrifying answer is both. And their scale surpasses anything humanity has ever conceived. First, let's talk about the cost, not in money, as currencies would have likely collapsed, but in resources. Experts estimate that building a minimal self-sustaining base for 10,000 people on the moon, along with the costs of research, development, and launches, would consume resources equivalent to tens of trillions of old world dollars. This figure is larger than the entire global GDP before Judgment Day. It's the total economic effort of an entire generation focused on a single gamble. Next is the transportation challenge. Let's use the most powerful rocket ever designed, SpaceX's Starship, as our unit of measurement. For crewed flights, each mission could carry about 50 colonists and their personal gear. Thus, just transporting 10,000 people would require 200 successful flights. But the people are the smallest part of the cargo. We need hundreds of thousands of tons of supplies, habitat modules, air and water recycling machinery, many nuclear reactors, giant 3D printers, rovers, mining equipment, seeds, and countless other devices. With a maximum payload of about 100 tons per flight, we are talking about thousands, perhaps tens of thousands more flights. The entire Apollo program had only 9 missions to the moon. Now, we would need to launch that many every week for years on end. And this is where logic begins to break down. Where does the supply chain for this miracle come from? These rockets don't just spring from the ground. They require advanced alloys, complex microchips, and millions of components manufactured in specialized factories around the world. But Earth is now a dying planet. The sky is choked with soot, cities are radioactive ruins, and the global transportation network no longer exists. How can you operate a sophisticated rocket engine factory when you can't find a stable power source, when your best engineers are struggling to find food and clean water? Manufacturing the most complex machines in history from the ashes of a collapsed civilization is an unsolvable paradox. Finally, there is the unavoidable risk. Even in the golden age of aerospace, failures happened. A 99% success rate sounds safe, but when you perform 1,000 launches, it means 10 tragedies. 10 fireballs consuming the most precious people and cargo. A minor error during landing, a micrometeoroid impact, a stuck valve in the life support system, all are death sentences. On the moon, there is no room for error and no second chances. Each flight is not just a technical gamble, but a gamble with life itself. The price of life on the moon is not just measured in resources, but paid for with the lives that will surely be lost along the way. When survival is the only ticket, what criteria will be used to decide who goes and who stays? This is no longer a hypothetical question from a movie, but the coldest moral and logistical problem humanity has ever faced. In theory, the answer seems simple. We would choose the best and the brightest, a dream team for humanity. Engineers who can build and repair everything from air scrubbers to nuclear reactors. Surgeons and geneticists who can deal with unprecedented diseases in low-gravity, high-radiation environments. Geologists who can find precious resources beneath the barren lunar soil. And, just as importantly, agronomists who can turn ice and regolith into gardens that feed a generation. Physical and mental health would be screened to an extreme degree. There is no room for chronic illness, no room for psychological weakness. Each individual must be a perfect physical machine and an unbreachable mental fortress. But that's the theory. What about reality? The harsh reality is that this evacuation project costs tens, even hundreds of trillions of dollars. Where does that money come from? From superpower corporations, from billionaires whose wealth exceeds the GDP of many nations. Would they be willing to fund a trip that has no room for themselves, their families, or their loyalists? Human history suggests the answer is almost certainly no. The selection process would quickly devolve into a brutal political struggle. Instead of a list based on talent, we would likely see a list based on power, wealth, and connections. A brilliant engineer from a developing country might be pushed aside to make way for a tycoon's son. A world-class doctor might lose their spot to an influential politician. This is when the survival lottery begins. Who would have the final say? A global UN committee, or a secret council of those who hold the money and the technology? This question is even more terrifying than the nuclear winter itself, because it exposes the true nature of power and inequality that has always existed in our society. And this leads us to the core issue, the ethics of the choice. Is selecting a small group to survive, regardless of the criteria, the ultimate act of betrayal against the other 8 billion people? Imagine the day the list is announced. It would not be a day of celebration, but a day of global despair and outrage. The chosen would become targets of hatred and violent attacks. The launch facilities would have to be protected like impregnable fortresses, not against external enemies, but against their own kind. The psychological burden on those who leave would be unimaginable. They are not heroic explorers, but guilt-ridden survivors. Every time they look at the pale blue Earth dying through the window, they will see the faces of the billions they left behind. They will be the ghosts of a dead world, forever haunted by the price of their own survival. But this ship carries more than just people. It must also carry the legacy of an entire planet. This is Noah's Ark, high-tech version, and its cargo is more precious than its passengers. First and foremost is a gene bank. Millions of cryogenically frozen human embryos, carefully selected to represent the full genetic diversity of humanity, from every race, every ethnicity. Alongside them, the DNA of millions of Earth's animal and plant species. From the genome of the blue whale to the honeybee, from the giant baobab tree to the grains of wheat that sustained us. It is Earth's biological blueprint, a flicker of hope to one day recreate a part of the lost world. Next is the cultural heritage. A massive digital data archive, an immortal library of Alexandria. It contains all of humanity's scientific, historical, and literary knowledge. Every mathematical formula, every engineering blueprint, every work of Shakespeare, of Wendu. It also contains art, from Beethoven's symphonies to Bob Dylan's songs, from Da Vinci's paintings to classic films. It contains our soul. Why carry all this? Because without it, the survivors would be just a group of existing organisms. They might live, but they would have lost their identity. Rebuilding civilization is not just about building shelters and growing plants. It's about remembering who we are, where we came from, and the beauty we once created. Without history and art, humanity on the moon would be a flawed copy, a pale shadow of its former self. Ultimately, the selection is not just a problem of skills or money. It is a test of humanity. It forces us to confront the question, what is truly worth saving? Just the physical bodies, or the soul and legacy of a species? The answer to this question will determine whether the journey to the stars is a new beginning or merely the final chapter in the tragedy of humankind. Having escaped the radiation on Earth, could humanity fall into another deadly trap from space? The answer, terrifyingly, is yes. Fleeing the nuclear hell of our own making, humanity would face enemies far more ancient, relentless, and unpredictable. Enemies born not of weapons, but of the very fabric of the cosmos.
First, let's talk about the silent killer, galactic cosmic rays, or GCRs. Imagine an invisible rain of hypodermic needles, never stopping, coming from every direction in the universe. That's GCRs. They are subatomic particles, mostly protons and helium nuclei, accelerated to near the speed of light by distant supernova explosions millions of light years away. On Earth, we are protected by a near-perfect two-layer shield, our magnetic field and our thick atmosphere. But the Moon has neither. It is naked. With no magnetic field to deflect them and no atmosphere to absorb them, this deadly rain pours directly onto the surface. Unlike nuclear fallout on Earth, which decays over time, GCRs are a cruel constant. Every second, every minute, every day, the bodies of lunar settlers would be pierced by hundreds of these high-energy particles. They rip through DNA strands, causing relentless microscopic damage to cells. In the long run, the consequences are unavoidable. Cancer risks would skyrocket. Cataracts would be almost a certainty. But most frightening is the damage to the central nervous system. Studies have shown that prolonged exposure to GCRs can impair cognitive function, cause memory loss, and slow down decision-making abilities, skills that are absolutely critical for survival in such a harsh environment. The dream of a new beginning could turn into a slow-motion death sentence, a countdown to the day your body and mind betray you. But if GCRs are the slow torturer, the universe has another executioner, one that acts with lightning speed and far more brutality: solar particle events, or solar storms. Our Sun, the source of life for our planetary system, sometimes turns into a raging monster. Massive coronal mass ejections can hurl clouds of plasma and high-energy particles into space at horrific speeds. If such a storm were aimed at the Moon, the settlers would have only a few hours, or perhaps even just minutes, to react. An alarm would blare throughout the base. It wouldn't be a drill. It would be a race against death. Everyone would have to immediately seek shelter in specially designed storm cellars, rooms shielded by meters-thick layers of lunar soil. Anyone caught outside, on a rover on a mission, or repairing a solar panel would face a terrible death. The amount of radiation in a powerful solar storm can be equivalent to thousands of X-rays at once, enough to cause acute radiation syndrome and an agonizing death within days. Existence on the Moon would be tied to a constant fear of the Sun's sudden wrath. But the most insidious enemy, perhaps, comes not from the distant stars or the fiery Sun. It lies right under their feet. It's the lunar dust, also known as regolith. This is not the soft, loamy dust from home. After billions of years of bombardment by micrometeorites in a vacuum, with no wind or water to erode it, the lunar soil has been pulverized into extremely fine particles, as sharp as broken glass and highly abrasive. To make matters worse, due to the effects of solar radiation, these dust particles are electrostatically charged, causing them to cling to everything, from spacesuits and gloves to equipment and interior surfaces of the habitat. The Apollo astronauts got a taste of this. Lunar dust snuck into the lander, causing lunar hay fever with symptoms of sneezing, itchy eyes, and sore throats. That was after only 3 days of exposure. Imagine living with it for years. This dust can wear down rubber seals, jam mechanical joints, scratch helmet visors, and damage delicate electronic equipment. It is an engineering nightmare, but the real danger is when it's inhaled. These sharp particles can embed themselves deep in lung tissue, causing chronic inflammation and irreversible damage. In the long term, it could lead to severe respiratory diseases like silicosis, a slow and painful death. The settlers would have to fight a relentless war to keep this microscopic invader out. Every entry and exit through the airlock would be a complex decontamination procedure. But it would only take a moment of carelessness, a tiny tear in a suit, for this invisible enemy to flood in, turning their lungs to stone. So, the escape from Earth is merely a trade-off. They would exchange the threat of man-made bombs for the eternal hazards of the cosmos. A radioactive prison where the walls are GCRs, the storms are SPEs, and the floor is a layer of toxic dust waiting. Can the human mind and body truly endure such a life? After many generations, could children born on the moon still be considered Earthlings? This question isn't merely about birthplace, it strikes at the very core of human identity. Escaping the cradle of Earth is not just a migration, but a forced evolution, a permanent transformation of both body and mind. And those changes might be even more terrifying than the nuclear winter they left behind. First, let's talk about the body. For millions of years, every cell, every muscle fiber, every piece of our bone has been sculpted by an invisible yet omnipotent force, Earth's gravity. Our body is a perfect machine for operating at 9.8 meters per second squared. But on the moon, with only 1/6 the gravity, that machine begins to silently malfunction. The skeleton, no longer bearing its usual load, will begin a process of demineralization. Bone density gradually decreases, making them as brittle and porous as a dry sponge. This isn't the common osteoporosis of old age, but a systemic degradation, turning healthy young people into fragile individuals. A light fall on the moon might be fine, but if they were to return to Earth, their skeletons could shatter under their own body weight. The muscles suffer the same fate. The use it or lose it rule becomes relentlessly cruel. Despite rigorous exercise regimens, maintaining Earth-like muscle mass is nearly impossible. This is especially true for the heart, the most important muscle. In a low-gravity environment, it doesn't need to pump blood as forcefully against the pull, and it gradually becomes lazy and weaker. The circulatory system also changes. Body fluids shift upwards, causing the puffy face and bird leg phenomenon experienced by astronauts. More seriously, increased intracranial pressure can compress the optic nerve, causing irreversible vision problems. The immune system also becomes dysregulated, making the body vulnerable to pathogens that would otherwise be harmless. After a few generations born and raised in this environment, a new type of human will emerge. They will be taller, more slender, with weak skeletons and underdeveloped muscles. They will be creatures optimized for the moon, but for that very reason, they become its permanent prisoners. Earth, with its powerful gravitational pull, will become a death planet to its own descendants. The door back home has been sealed forever. But the physical transformation is only half the story. The real torture takes place in the mind. Imagine growing up in a cramped habitat under artificial domes. Your sky is not blue, but an endless, cold black, dotted with stars that never twinkle. And hanging in that darkness is Earth, a beautiful blue and white orb, now a symbol of loss, a dead paradise you can never set foot on. This is Earth separation syndrome, a generational sorrow, a cosmic-scale loneliness that gnaws at the soul. Life in a lunar colony is a state of perpetual stress. The constant hum of life support systems, the persistent fear that a tiny crack in a wall or a technical glitch could wipe everyone out, and the absolute isolation from the 8 billion people struggling below. There is no rain, no wind, no smell of damp earth after a storm. Everything is artificial,
controlled, and fragile. In such a small, closed community, the risk of mass psychological crises is extremely high. A single panic attack, a false rumor, could spread like a virus, turning the Ark of Salvation into an asylum in space. Over generations, these pressures will forge an entirely new society. A new culture will arise from the ashes of memory. Their language will change, creating new words to describe the feeling of floating in 1/6 gravity, or the terror of seeing a solar storm. Their art will no longer depict fields or oceans, but will portray the contrast between the darkness of space and the harsh, unfiltered light of the sun. Their religion might worship Earth as a lost deity, or curse it as the hell their ancestors had to flee. They will no longer be Americans, Chinese, or Vietnamese. They will be Moon people, Lunarians, with a shared identity built on survival and separation. They are the future of humanity, but a future completely severed from its past. They are living proof that sometimes, to survive, you must lose who you are. Before betting everything on the moon, have we overlooked any other potential escape routes? The lunar plan, while ambitious, is essentially a lifeboat, cramped, perilous, and only for a select few. But could there be larger vessels, safer harbors that, in our panic, we failed to consider? The answer is yes, and they take us to horizons both familiar and strange. The first and most obvious choice is Mars. The red planet has long been humanity's dream destination, not just for exploration, but as a potential second home. Compared to the Moon, Mars is a paradise. It has an atmosphere, albeit thin, that provides an initial layer of protection against radiation and micrometeoroids. A Martian day is nearly 24.5 hours long, extremely favorable for human circadian rhythms and agriculture. Most importantly, Mars is a resource-rich world. Beneath its red dust lies vast water ice, not just at the poles, but potentially everywhere. The atmosphere is filled with carbon dioxide, a resource for creating breathable air and rocket fuel for a return journey. In theory, Mars has everything we need not just to survive, but to build a self-sustaining civilization. It's not a temporary outpost, but a seed for a new branch of humanity. But a cruel reality stands in the way of this dream: distance. The journey to the Moon takes only 3 days. The journey to Mars, even under the most favorable conditions, takes 6 to 9 months. In a post-apocalyptic scenario, with Earth dying, such a long journey is almost suicidal. Each ship would be an isolated island, with no hope of rescue, no turning back. A minor technical failure, a sudden solar storm, would turn the vessel of hope into a coffin among the stars. Furthermore, resupplying and building the initial infrastructure from a collapsed Earth is unthinkable. Mars is a magnificent goal for humanity at its peak, but a terrible gamble for survivors trying to escape hell. If traveling to another planet is too risky, why not build a world of our own? This is the idea behind orbital stations, also known as O'Neill cylinders. These are not cramped space stations like the ISS. Imagine massive cylindrical structures, tens of kilometers long, rotating slowly in space to create centrifugal force, perfectly simulating Earth's gravity. Inside these cylinders lies an entire world. There is land, rivers, trees, cities. The sky would be sunlight controlled by giant mirrors, allowing for the creation of day-night cycles and seasons at will. This is the ultimate solution, solving all the problems of the Moon and Mars. No more worries about the effects of low gravity on the body.
No more fear of radiation, as the station's hull could be meters thick. We could create an artificial paradise, a perfect replica of Earth without natural disasters or war. However, just like Mars, this is a dream of a prosperous civilization. Building an O'Neill cylinder requires a colossal amount of matter and energy, equivalent to mining an entire asteroid. It demands a space-based industry that we, even before the cataclysm, had only begun to imagine. In the context of a devastated Earth, gathering enough resources to build even a miniature version of this paradise is pure fantasy. It's like a drowning person dreaming of building a luxury yacht. So Mars is too far, and an artificial paradise is too complex. We have been so busy looking up at the stars that we may have forgotten the most viable answer lies right beneath our feet. The third, and perhaps most rational option, stay on Earth but not on the surface. We would go underground. Instead of building domes on the moon, we would build self-sufficient cities deep underground or at the bottom of the ocean. This choice solves the most intractable problems. Earth's crust, with kilometers of rock or seawater for shielding, is the most effective radiation and nuclear winter shield the universe can offer. We wouldn't need to worry about adapting to weak gravity, as we'd remain in our familiar 1G environment. Energy could be supplied by geothermal power, a nearly limitless and stable source. Water could be drawn from vast underground aquifers. Logistically, this is a far more feasible plan. We don't need billion-dollar rockets, but rather drilling machines and tunneling technology that humanity has long mastered. In theory, we could save a far greater number of people than with any spacefaring plan. However, this is not an option without its downsides. Life underground would be an immense psychological challenge. No sunlight, no blue sky, only walls and artificial lights. It is a life of hiding, a resilient but claustrophobic existence, waiting for centuries for Earth's surface to become habitable again. It's not a romantic escape to the stars, but a silent struggle to preserve the flame of humanity within the heart of its mother planet. Thus, as we weigh the alternatives, a complex picture emerges. Mars is a promise for the distant future. An orbital station is a beautiful fantasy, but the underground shelter, though unglamorous, emerges as the most realistic solution, a final fortress for humankind. Perhaps in the race to find a new home, the wisest choice is not to leave, but to dig deeper into our old one, to protect it from within. So, after all this analysis, is the plan to evacuate to the moon a brilliant salvation plan or humanity's last great illusion? The answer, when faced with harsh reality, seems quite clear. This plan is not a life raft, but a mirror reflecting our limitations and our mistakes. Let's revisit the insurmountable walls. First is the economic and logistical wall. The cost to send a small group of people to the moon and sustain them would consume the entire remaining resources of a dying civilization. Transporting every single chip, every nutrient pack from an Earth plunged into nuclear winter is not a logistical problem. It is a series of impossible miracles. When supply chains on the ground have collapsed, how can we maintain an interplanetary one? Next, the biological wall. We escape radioactive fallout on Earth only to face an invisible yet more formidable enemy, cosmic radiation and solar storms. We can build thick walls, but we cannot build a perfect shield against the universe itself. The lunar dust, sharp as glass, will wear down machinery and destroy the settlers' lungs. And finally, the greatest wall of all, the ethical wall. The question, who gets to go, has no humane answer.
Any selection criteria, be it skills, health, or power, is a death sentence for the billions left behind. It would turn the Ark of Salvation into a symbol of ultimate inequality, sowing the seeds for humanity's final resentment and conflict.
So, if not a second Earth, what would a lunar colony be? Perhaps it could only be a living museum, a small, precious collection of what humanity once was. A few thousand people, a frozen gene bank, and a digital archive of our history and culture.
They would be the keepers of memory, living in isolated domes, looking back at a blue marble now turned gray with a single mission: to exist. Not to be reborn, not to expand, but simply to ensure the flame of human knowledge does not completely die out.
The moon is not a life raft for humanity. It is the black box, recording the data from a crashed spaceship called Earth. This leads us to a final truth, an undeniable verdict.
The immense effort, the brilliant minds, and the vast resources needed to build a tiny outpost on the moon would be infinitely better spent ensuring that no one has to leave Earth in the first place.
The greatest plan is not to flee a burning home. The greatest plan is to extinguish the fire. The solution to humanity's survival lies not in the cold craters of the moon, nor the red dunes of Mars. It lies here, in the hearts and minds of each of us, in our ability to choose peace over war, cooperation over division. The greatest journey is not the one among the stars, but the journey to overcome the limitations of ourselves. Because, in the end, we cannot run from who we are. The only home we truly have has always been Earth, and the responsibility to save it is ours alone.